topic 3.1, which is on seismic, hydroacoustic, and infrasound technologies and applications. So this topic was already featured yesterday for those of you who attended online to the event with one oral and 3 posters. Today we will have 4 more presentations, oral. And then on Thursday, the session will continue with poster session 3.1. The lightning talks will be in the Wintergarten at 11, and then it will be followed by the poster session at 12 on Thursday. Already at the SNT 2023 and this SNT again, the level of interest is very high, it seems, especially around data quality assurance and control. We have about half of this year's presentations that address calibration and metrology, with seismic applications receiving an increasing attention. I would like also to highlight a dedicated side event on metrology, which will take place tomorrow morning from 9 to 12:30 in the same room. This event will provide a deeper dive into the calibration and traceability issues, which are central to many of the contributions in this topic 3.1. During or after the session, please use the mobile application to vote for your favorite presentations. All these votes will then be accounted for on Friday to award the best presentation prize. So now I think with that being said, we can begin with our first presentation by Samuel Christoffersen to speak on infrasound uncertainty propagation, ensuring traceability from the laboratory to the field. Please, Samuel.
Okay, great, thanks. Thanks for the introduction. So I'm going to talk about infrasound. I guess we've lost the slides. I'm going to talk about infrasound calibration, and in particular, the abstract I submitted is going to be a little bit different than that. So I'm going to be talking about calibration of domes being used for wind noise reduction systems, and comparing that a bit with the results of the Rosette-style wind noise reduction systems. So just brief outline, and give a bit of introduction, and talk about how to do on-site calibration, as well as talk about the noise reduction, comparing the dome and the Rosette, as well as talking about how the infrasound, the calibration of the domes affects or propagates through to the measure end, so our observations in azimuth and speed. So basically, metrological traceability is the idea that when we have our measurements, typically with a microbarometer, we want to measure pressure in pascals. Usually we end up getting a value in volts or in counts. So what we have to do is then figure out how to convert that to pascals. And so the idea with metrological traceability is that we have these various levels: primary, secondary, field calibration, and finally in situ or on-site calibration of our sensors that allow us to have a traceable calibration back to these SI units, pascals in this case. And I think the thing that I want to focus on as well with this talk is both that on-site in situ calibration, but then also what impact that has on what we're really interested in, because I mean, from a CTBT perspective, we're interested in back azimuth trace velocities, the direction of arrival. And so when we make those measurements of back azimuth trace velocity, what are the effects of the calibration uncertainties on those measurements? And so for wind noise reduction systems, basically they've been put in place to battle basically one of the biggest problems biggest challenges, I should say, for infrasound measurements is wind-generated turbulent noise. And so there are these wind noise reduction systems. For example, in the top picture, we've got this Rosette-style one, which is sort of a standard, gold standard, one could say, and is what is installed at, I believe, most of, if not all of the IMS stations. And basically, this averages that sort of turbulence over an area that's larger than sort of the turbulent eddy size, so then we greatly reduce the impact of that noise. Another method that's I think being studied more and used more and more are these domes. So for example, that picture on the bottom is a 2.4 meter metal dome diameter. And the idea of the dome is similar. It kind of breaks the eddies up and averages them out over the surface of the dome. And so then we get that reduction in noise. And so in order to calibrate these on site, we have to bring out a reference sensor, so just a reference microbarometer, and then that's co-located with, for the wind noise reduction, or for the rosette style, we just co-locate it with the Berry center of the wind noise reduction system, and then we can do a calibration by comparison to get a measure of what the response of that wind noise reduction system is, so that rosette, those pipes are. For the domes, one thing that is slightly more complicated. So with the rosette, I mentioned about it having to be near the Berry center, so that's of the wind noise reduction system. And that's important because if there's a shift in the position of the reference sensor, then that will result in a phase error in the calibration, which would bias our calibration and then bias our ultimate measurements, which obviously we don't want. If we put a reference sensor right next to the sensor under test, so that's that sort of green star there, it'll be under the dome. It's no longer going to be a reference sensor in that case. And so what we had to do is we had to place our reference sensors, basically put 4 of them symmetrically outside the domes to sort of avoid too much of an impact from the domes on the turbulence and on the acoustic signals, so that we'd have sort of clean reference signals, so to speak. And then the idea is for the phase shift, what we do is we basically create a virtual reference. So by taking the average of those 4 reference sensors, that creates a vertical reference that will be centered on the microbarometer, that green star. And that allows us to get the phase shift. And then for the gain, we can't do that because when we average those 4 sensors, that's going to have an impact on the gain of that virtual sensor. So I end up doing a reference to each sensor individually, or a calibration to each reference sensor individually, and then average that to get the gain. And so the next step is to think about how do we make these wave parameter estimations. So for those of you who most of you are probably fairly familiar with this, but I'll just go over quickly the idea. Basically is using the time delay of arrival. So we use this progressive multi-channel correlation, or PMCC, detector and estimator, and it basically uses the arrival times, difference in arrival times at each of the sensors in the array, and then we're able to make an estimate of the azimuth and trace velocity. And because it relies on arrival times, that means it's very susceptible to phase error. So that means that the phase calibration is very important for our wave parameter determination. So quickly here, just show a bit of what is sort of the added or the effect on noise for sort of both these systems. So we have the blue line is showing the ratio of the rosette PSD to a reference sensor power spectral density. And so basically that gives us a sort of an estimate of how much reduction we're getting in noise. This is for an 18-meter diameter rosette with 32 inlets. So this isn't a standard IMS style rosette normally with more like 96 inlets, so the noise reduction isn't quite as good. The yellow line is just so if you notice with the blue line, we have the resonance peak that shows up, but that's not really a peak in the noise, so to speak, because really we're interested in signal to noise ratio, and since that's more of an impact on signal as well, I deconvolved the transfer function, or corrected for the transfer function of the rosette, and that gives us the yellow line. And so we can see that that kind of reduces and then comes back up, sort of approaches to 0 decibels at higher frequency. And then we can see that the orange is showing an example of this is with that 2.4 meter dome that I'd shown in that picture. And so we can see that the frequency range in which they're effective is different, and it depends largely on the size of the rosette or the dome. And so now into some of this calibration. So I did two calibration experiments. One was using a loudspeaker source. So we had a loudspeaker. It was in this sort of wooden baffle that gave a bit sufficient back pressure area for it to generate an infrasound signal down to a few hertz. And it was reasonably pure, especially when we started getting up into higher frequencies around 10, 15 hertz worked pretty well. And we can see we tried this with several different domes, between about 30, 40 centimeters up to about a 1.8 meter diameter dome with different materials. And in all of these cases, up to about 40 hertz, we didn't see any measurable deviations in the gain or in the phase shift. So that's a good, promising result. And the next step was to look at this same dome calibration in the using this Gabrielson method, sort of just in the field. So we had a dome out in the field somewhere in France, and we just let it run the calibration for several weeks to generate enough signal to perform the calibration for, I think it was 8 days worth of data. And we can see here the blue is showing the results relative to the virtual reference, and we can see that, like I say, that gain goes up, but that's in the blue, and it stays flat in the yellow, which is the comparison with the average of each individual reference calibration. But that blue curve going up is because we've artificially decreased or there's basically a transfer function associated with that virtual sensor. So it's not actually the sensor under test or the dome. And we can see that when we do the mean references that we get a flat response. And then what's perhaps, from my perspective, perhaps more interesting is seeing the phase response. So I've never seen any studies looking at the phase response of these domes. And we can see up to about 20 hertz or so, that's phase response stays basically null within the uncertainties that we have. And so that's a good sign. So that means that we're seeing the dome doesn't have an impact on the amplitude or the phase of the acoustic signal. And finally, I want to discuss what are the impacts of that calibration on our observations, so our azimuth and trace velocity estimations. And so what I did here is I took that dome calibration that we did in the field in France and then said, okay, imagine if we had that dome at a station. For example, I used IS-26. If each sensor was that dome set up and had that corresponding uncertainty, what would the uncertainty be in the azimuth and trace velocity? And so we can see I've got, for reference here, we've got the blue curve shows what the calibration or what the uncertainty response is for rosette calibration. The red is a dome. And then additionally, I have the theoretical uncertainties associated with 0 dB, 10 dB, and 20 dB in yellow, purple, and green. And what I guess important takeaway here is that we can see one is that when we look at the dome and the rosette, we're seeing similar calibration or similar uncertainties related to the calibration. So that's a good sign that we're not degrading our results substantially by using a dome versus a rosette. And then the other thing is both the rosette and the dome fall within sort of between an equivalent of between 10 and 20 decibels signal to noise ratio. And I mean, a 10 to 20 decibel signal is a pretty high signal to noise. So basically we're still in that region where SNR is going to be the big battle, and the calibration is not going to be our a main contributor to uncertainty. And so basically, just to wrap up, we saw that with the 2.4 meter metal dome, we saw negligible phase shift up to about 20 hertz or so within the entire IMS band of interest. The uncertainties were similar to that of an 18-meter rosette, as well as being between 10 and 20, between the equivalent of 10 and 20 decibels of SNR. And it would be interesting to do further calibrations of different dome sizes and styles to see if this remains consistent, particularly if you start increasing the dome, will that have an effect on the higher frequency bands? And I guess I'll just, Benoit already mentioned it, but I'll just give a little plug again for the metrology side event that we're having tomorrow morning at 9 o'clock in here. So thank you for your attention, and I'll take any questions.
Okay, do we have any questions for Samuel?
All completely clear? Okay.
All clear? So I'd just like to ask you, Samuel, these domes have been kind of proposed for some time. They've been an alternative to rosettes. How far do you think they are along its development cycle where they could actually be used routinely? You say there's more work to look into.
Well, I mean, in terms of them being used, I think that there's a lot of like more regional stations or national stations that are starting to use those. In terms of calibration, I haven't seen any real like complete calibration analysis like this. So I think that that's something that would be useful to do for some of these different domes, particularly, like I said, if you start having, like for a 2.4 meter dome, that's pretty small, so we might expect that, okay, there's an effect, but it's just too far up in frequency and we don't see it. But if you had maybe a 10 or 15 meter dome, I don't know if people are using quite that large, but I think up to 8 meters has been used, and maybe that would have an impact, start having an impact on the infrasounds region. But that would be further studies that would be interesting to do.
Okay, thank you. Any other questions? We've got time for one more. Yeah.
Out of curiosity, what do you believe would happen to the uncertainty propagation if you change to 3 transducers instead of 4?
If you use 3 references?
Yeah.
Well, I guess it would be, if you set the references up sort of like in a triangle so that it's centered at the microbarometer, I think it would probably, I mean, I think you could probably do it with 2 as well, as long as you had it set up. The advantage of 3 would be there would be a little bit more isotropic. That would probably be more efficient in terms of it would require less sensors. I don't know exactly whether that would have a huge impact on the calibration results. It might, you'd have 1 less sensor, so it might sort of increase the uncertainties a little bit, but I think it would be not a huge difference.
Thank you.
Okay, thank you very much, Samuel.
Thank you.
Thank you, Samuel.